Okay, so hi everybody. Thanks for listening in. In this presentation, I want to talk to you guys about Venus. Now, in many ways, Venus is very similar to Earth. It has about the same density as Earth. It's about the same size, so it has about the same mass. That implies that Earth and Venus have many similarities in their internal structure and various other aspects. And in fact, Venus is called Earth's twin for that reason. However, the environment on Venus's surface is radically different from the Earth. We've already talked about how Mars's surface is different from Earth's and is quite inhospitable to Earth life. Venus takes that to a different level. Venus's surface temperatures are up to 740 Kelvin or 900 degrees Fahrenheit, which is hot enough to melt lead. Furthermore, Venus has such a thick atmosphere that the surface pressure is 90 times higher than Earth's, which is comparable to being 1 kilometer underwater. So if you want a spacecraft to work on Venus, it has to basically be able to cope with being put at the bottom of the ocean and set on fire. Not to mention there's sulfuric acid on Venus. So this is a very hostile environment. Now, despite that, there are spacecraft that have been to the surface of Venus, and all of 4 of them have returned pictures. So as opposed to Mars, where we have all these beautiful pictures, we have literally 4 pictures of the surface of Venus. They were all taken by Soviet space probes called Venera that reached the surface basically in the 1970s. These are the first 2 pictures returned from the surface of Venus, and you can see it's got a bunch of rocks on it. But the big question then becomes, why is Venus's environment so different from Earth's? Well, to understand that, we should be a little more explicit about what these differences represent. Now, temperature is relatively easy to understand. Remember, temperature is random motions. So if something's a higher temperature, it means the molecules in the atmosphere are moving faster. The other point, though, is what is atmospheric pressure? It's basically how much the atmosphere is pushing on us. But what sets that? Well, one thing that sets that is temperature. It's how fast things are moving. But the other thing that sets it is just how many molecules there are in the atmosphere. The way to think about it is this. If you held a sheet of paper horizontally, there is an atmosphere's worth of material weighing down on that paper. But the paper doesn't sag under that weight because there's atmospheric pressure. There's air below that paper pushing back up. So atmospheric pressure is basically equivalent to the weight of the atmosphere above it. So it turns out that on Earth, the atmosphere's weight is about 15 pounds per square inch. So it's not trivial. But on Venus, it's 90 times higher. So there's 90 times more molecules in the atmosphere. It just weighs 90 times as much, which is the same thing because Venus and Earth have similar gravity. And those molecules are moving around faster. Okay? And the question is, why? Why is the atmosphere of Venus so hot and so dense? Let's worry about the hot part first, because most people will have a natural explanation for this. Venus is hot because Venus is closer to the sun, which is true. You know, Earth is at a distance of 1 astronomical unit from the sun. Venus is 0.72 astronomical units from the sun. So it's considerably closer. And that means the sun is much brighter to Venus than it is to the sun. Remember, brightness drops off like 1 over distance squared. So the brightness of the sun at Venus is 1 over 0.72 squared times its value at Earth. That works out to be about a factor of 2. So the sunlight falling on a square meter of Venus is 2 times more than the intensity of light falling on Earth. And you might go, well, Earth's temperature is, turns out, 290 Kelvin. Venus's temperature is around 740 Kelvin. That seems like it's about right. It's not quite that simple. The thing is, it isn't just that sunlight is hitting these objects and warming them up. That's not the only process involved. These planets are also radiating energy because they're at a finite temperature. So as sunlight falls on these planets, yes, they do get warmer and heat up, but by being warm, they emit their own radiation. So there's energy coming in from the sun and energy going out due to its thermal radiation. And the question is, when do those balance? Because a planet will heat up until the amount of heat it radiates equals the amount of heat it receives. And the key thing to understand here is that the amount of energy an object radiates due to thermal radiation is a strong function of temperature. These are those plots of black body radiation, which again is something you could just calculate from temperature. And as you go to higher temperatures, the peak of this curve shifts to shorter and shorter wavelengths. But in addition, it just gets brighter. And it turns out that the amount of energy an object emits, if it's a black body, is a constant times the temperature raised to the 4th power. That means temperature times temperature times temperature times temperature. So if you double the temperature of something, it emits 16 times more energy than it did. So you have to account for this. Now, you can do this. You can calculate the energy flux from the sun and the thermal radiation from the planet under the assumption they're black bodies, and calculate what temperature balances the energy input and output. And if you do that for the Earth, you get a fairly sensible number, around 278 Kelvin, about 40 degrees Fahrenheit, which isn't too far off the actual answer. For Venus, though, this doesn't work. Venus, you do that same calculation, and it's a bit warmer. It's 327 Kelvin, but that's 129 degrees Fahrenheit, which is uncomfortably hot, but not 740 Kelvin, which is 900 degrees hot. And this assumes that these objects are black bodies, which is not true. These things reflect light. They don't just absorb all the light from the sun, they reflect a fair fraction of it. Earth reflects about 30% of its incident sunlight. That's why it's bright. Venus is even more reflective, mostly because it has more clouds, and reflects about 75% of its incident sunlight. That means that energy is not available to be absorbed and heated up the planet, which makes them even colder. On Earth, the temperature that you would predict, if you accounted for this part, drops to about 255 Kelvin, which is below the freezing point of water, which means all of our oceans should freeze. If you do it for Venus, since Venus is so reflective, you get minus 40 degrees. you get that Venus is colder than Earth, which isn't right. So this is missing something very important, which is a fundamental property of atmospheric physics called the greenhouse effect, which you have certainly heard about. All the greenhouse effect is basically something that arises because the molecules in the atmosphere of Earth interact with light at different wavelengths in different ways. For example, on Earth, we have visible light from the sun. Visible light doesn't interact much with the atmosphere. The atmosphere is transparent to visible light. So most of this light just gets onto Earth and gets absorbed. But the Earth doesn't emit visible light. It emits infrared light because it's colder. Turns out certain molecules in Earth's atmosphere interact very strongly with infrared light and cause it to bounce in different directions. So thermal radiation from the Earth gets scattered by the molecules in our atmosphere. A fraction of that gets scattered back to Earth. So the light can't escape Earth as quickly as it can be absorbed. This raises the temperature of Earth. Now, the way it raises temperature, how much it does so, depends on exactly wavelength at temperature. So here's another way to look at that. These are plots showing how well different molecules in the atmosphere absorb light. Here's oxygen and ozone, here's carbon dioxide, here's water. Now, the atoms that are most prevalent in our atmosphere, which are nitrogen, argon, and oxygen, interact with light not very well at all. And this is a plot of how much is absorbed as a function of wavelength. Over here we have the visible, over here we have the infrared. Things like oxygen don't interact very well at most wavelengths. So the atmosphere is pretty transparent to visible light and pretty transparent to infrared light. Carbon dioxide and water, on the other hand, are pretty transparent at visible light, but are not at all at infrared light. And this is what leads to the greenhouse effect. Earth is trying to emit its radiation at around about 11 microns, with a bit of a spread. So this is in the middle of these absorption bands for carbon dioxide and water. Since these are not places light can get through very well, the temperature has to go up to compensate. That allows more light to get out, but also shifts the peak to longer wavelengths. And on Earth, going from about 240 or 250 Kelvin up to 285 allows enough light to get through around 10 microns, or micrometers to be specific, to escape and balance the books. So that's why Earth's temperature is warm enough to support liquid water, which is important. Now, as we're changing the carbon dioxide content of our atmosphere, we're pushing this. We're not pushing it much. We might change it by another couple of degrees, but that's enough to significantly affect our climate. Now, on Venus, we have an extremely extreme example of this. And the reason for that is Venus's atmosphere isn't mostly nitrogen, argon, and oxygen, which are the dominant constituents of Earth's atmosphere and don't interact with light much at all. This is a table showing the percentage of molecules in each atmosphere. On Earth, it's 78% nitrogen, 21% oxygen, both of which are fairly transparent at the infrared. There's a little bit of carbon dioxide and a little bit of water, which are enough to affect our temperature by some amount. Venus's atmosphere is 96% carbon dioxide, which means the greenhouse effect on Venus is very effective. It is so effective, it basically forces the temperature of the planet to increase to the point that it can emit through this gap around 4 microns. This drives the temperature from something vaguely around the freezing point of water up to a temperature that can melt lead. So the reason Venus is so hot is primarily because it has this extremely dense carbon dioxide rich atmosphere. But that raises a completely new question. Why is Venus's atmosphere so different from Earth's? They're similar in their bulk densities and sizes. Shouldn't they have similar atmospheres? Well, to answer this, we need to take a closer look at these two atmospheres. And not just look at the percentage of molecules in each atmosphere, but look at the total number of molecules in both. So I could write this in terms of total number of molecules, but those would be ridiculously big numbers. So I'm just writing them here in units of 1 Earth atmosphere. So Earth has 0.8 Earth atmospheres of nitrogen, 0.2 Earth atmospheres of oxygen, and some amount of argon, carbon dioxide, and water. Okay, in that case, what about Venus? Well, Venus has 90 times Earth's atmosphere. So you have to multiply these numbers appropriately. And what you find is, okay, it has a bit more nitrogen, but they're kind of close, 3 versus 1. They have the same kind of amount of argon, 0.006, 0.009. The real radical differences are Earth has 100 times more oxygen, and Venus has 100,000 times more carbon dioxide. So this is the difference we have to explain. Now, there's a natural explanation for both of these. Why does Earth have more oxygen? Well, because Earth has life. The oxygen in our atmosphere is from plants. Plants take carbon dioxide and water and convert it into wood, stems, various solid materials, which produces oxygen as a byproduct. Now, if plants die, you can reverse that process by burning them, which turns all of those complex molecules and oxygen back into carbon dioxide and water. But what this is doing is producing oxygen. And the fact that there's oxygen in our atmosphere is basically generated by life. But in addition to producing oxygen, processes like this also remove carbon dioxide. Turns carbon dioxide into wood, which is a solid, which might turn to coal or oil, which are liquids and solids. And this is not the only way that can happen. Carbon dioxide can react with water to produce rocks, known as carbonates. This happens on Earth often due to life. Various living creatures create minerals from carbon dioxide and water in oceans. But it can also proceed without. Now, if you took all of the carbon that is locked up in these sorts of carbonate rocks and trees and in coal and oil and all of that and put it into the atmosphere, you would get about 90 times Earth's current atmosphere. So the difference between Earth and Venus is that the carbon on Earth is locked up in rocks and life, whereas on Venus, it's in the atmosphere. Now, the question becomes, wait, why is that? Okay, Venus doesn't have life, but this isn't clearly life connected, so what's going on here? Well, to answer that, we have to go back to the water. Earth and Venus have similar amounts of water in their atmospheres, but Earth has most of its water in ice and oceans. And in fact, if you took all of Earth's oceans and put it in the atmosphere, it would be 280 times the mass of our current atmosphere. So Earth has a lot more water. So the implication is Venus lost its water somehow. And it's fairly natural that it would do that. If Venus was hot, its water would be more likely to be in the atmosphere than in liquid form. And if you put water in the atmosphere and make it too hot, it can get lost. How does it get lost? Well, it gets high enough that ultraviolet light can break it apart and turn it into hydrogen and oxygen. Hydrogen is a fairly light atom. It just has a single proton in its nucleus. So it is actually light enough that it can escape Earth or Venus's gravity. So the suggestion is Venus has lost its water somehow and thus lost its ability to turn its carbon into solid form. And there's actually evidence for this. And it comes from looking at the tiny amounts of hydrogen left in Venus's atmosphere. Hydrogen comes in a couple of different types. Normal hydrogen just has a single proton in its nucleus. But there are types called deuterium, which have a proton and a neutral particle called a neutron. These have the same chemistry. They both form water, but they have different masses. So water that has deuterium is often called heavy water. Now, this second type of hydrogen atom is rare. On Earth, only about 0.00015 of hydrogen atoms are in this form. So less than 0.01% of hydrogen. On Venus, it's more like 2%, so about 100 times higher. Now, the thing is, if water is escaping, it's easier for lower mass particles to escape than higher mass particles. So if a bunch of hydrogen escaped, that would naturally leave something that was enriched in the heavier stuff. And this is cited as evidence that Venus had water, but it escaped. And this is the basis for our current understanding, which is basically a story where two planets start off very similar, but follow very divergent paths. So what we imagine is when they formed, Earth and Venus had very similar atmospheres, corresponding to very similar compositions. These gases are released by volcanoes, impacts, etc. And so when they start out with, their atmospheres have similar amounts of water, carbon dioxide, nitrogen, etc. But then they start to diverge because Venus is a little closer to the sun than the Earth is. What that means is Venus is a bit hotter than Earth. What does that matter? Well, if they have water, that starts, since it's hotter on Venus, it starts to get more humid. More of the water can be in the vapor phase as opposed to the liquid phase. But if you put water into the atmosphere, water is a greenhouse gas. It tends to make the surface hotter, which puts more water into the atmosphere, which makes it hotter. This is what's called a runaway greenhouse effect. It just basically causes the entire water budget on Venus to go into the gas phase. Now, that water is in the atmosphere. It can be broken apart and turned into oxygen and hydrogen, and the hydrogen escapes. So there's no way to recover that water. There's no way for the water to react with carbon dioxide to bring the carbon dioxide into solid form. So Venus goes through a runaway greenhouse effect and ends up with an atmosphere that's pure carbon dioxide. Earth, that never happens. It stays moderate, its oceans stay around, it allows the carbon dioxide to be turned into rock or stay in rock, however that goes. And so we end up with two planets that started off very similar, but due to a slight difference in solar flux, ended up with radically different environments. So that's a nice result. It's then interesting to ask, wait a minute, what about the surface of Venus? Okay, the atmospheres are radically different, but they should have similar surface properties, because why would geologic activity or tectonics or volcanism care about all of this stuff? And this is honestly a reasonable thing to think. The surface of Venus should be just like the surface of Earth, just with the oceans boiled off. And that's something people have wanted to study. It's a challenge, though, because Venus's atmosphere is so thick and so cloudy that whenever you take a picture of it invisible, all you see is clouds. You need to use other wavelengths to see the surface. And to see the surface clearly, you need something that can look through clouds, which is radio wavelengths. Now, to date, our best measurements of the surface properties of Venus come from the Magellan spacecraft, which contained basically a radar system which bounced radio signals off the surface to map it. And it generated this map. This is just a map of how reflective the surface is at radio wavelengths. It's often also shown like this, which shows the topography, where blue regions are low, red regions are high. I want to make it clear that this is not a picture of the color of Venus's surface. We only have 2 pictures of Venus's surface that actually are in color. These are again from the Venus spacecraft. And what you will see here is the surface is generally yellow. Now, looking at this surface, the way it's colored, you might naturally say, oh, this does look a little like Earth. There are regions like Ishtar Terra and Aphrodite Terra, which kind of look like continents. They're elevated regions and they're about the right size. Aphrodite Terra is about the size of Africa. Ishtar Terra is about the size of Australia. But if you look more closely, there's radical differences between this and Earth. If you look at Earth's topography, what you see is a very clear dichotomy. You have land, continental crust, and you have the stuff under the oceans, the oceanic crust. And it's not the color scale here. This is what happens if you plot how much of the Earth has different elevations. There's 2 distinct peaks. One is due to all the oceans, one is due to all of Earth, all of the continents. That's not what we're seeing here. Turns out everything here is a gradual transition. There are high points and low points, but there's not a clear dichotomy. Now, the dichotomy on Earth is due to plate tectonics. So this is indicating something's different again. And that persists if we start looking at specific geologic features. Now, some of these geologic features, particularly Ishtar Terra, look a lot like continents. This is a close-up of Ishtar Terra in topography. This is in radar. It is surrounded by mountains. Those kind of look like the edges of a plate. But this is the one place where that kind of sort of happens. We do see other tectonic features like Beta Regio here, which has a strong fissure going through it, indicating there is tectonic activity. And there are volcanoes in various locations. And there are actually a lot of volcanoes on Venus. There are a wide variety of different volcanic landforms scattered over the entire planet. But this is, again, a difference from Earth. On Earth, remember, volcanoes are concentrated along lines corresponding to boundaries between tectonic plates. On Venus, they're found all over the place. This again suggests that unlike Earth, Venus doesn't have plate tectonics. We've already said Mars also doesn't seem to have plate tectonics. The implication is the geology of Earth, which is dominated by these moving plates, is kind of unique to Earth. And why that is still a matter of some debate. So there are clear differences in the geology and the geologic activity on Venus. But then there's the question, what is the level of activity on Venus? Is it comparable to Earth or is it not? Well, the trick is, the way to understand that is to date the surface of Venus, which is hard because we can't collect samples there yet. The only way people have been able to think about this is to look for impact craters. And there are impact craters on Venus. This is a few examples of them. If we can look to see if the surface of Venus is heavily cratered or lightly cratered, or if there are regions of different cratering densities. And it turns out Venus is actually fairly lightly cratered. This is literally all of the craters on Venus, shown as little circles on this map. The average density of those craters, assuming impact flux similar to the moon, is around 500 million to 1 billion years old, which is close to kind of the average of Earth rocks, honestly. But the other thing is, there's no clear pattern to this. There aren't clearly terrains that are obviously older or obviously younger, indicating that there isn't this, again, distinction between like continental crust and oceanic crust, which on Earth have different average ages. Now, part of this is because there just aren't many craters, which is exacerbated by the fact that the atmosphere is thick, and so smaller craters just can't form. But it does suggest that Venus's activity does kind of operate in a different way than Earth's. Still leaves open the question of whether Venus is active today. And that is something people are very interested in, but have a hard time answering. And it's simply because we can't monitor the surface like we could with Earth or Mars because of this thick atmosphere, and that radio antenna is no longer in orbit. But there's some intriguing hints of this. First of all, it turns out we can't see Venus's surface very well in the visible. We can get glimpses of it in the infrared. Down here, we have a plot of how much the surface of Venus emits light at 1 micrometer. This is actually incorrect. It shouldn't be millimeter, it should be micrometer. And what you can see is there are spots that emit better. These turn out to be high elevation regions. This is a map showing topography, the same region. And again, red is high, blue is low. So regions like this are at high altitude and emit differently. That's not because they're hot, they're actually cooler than normal, but implies they have a slightly different composition, which might be because they haven't been in the atmosphere as long and so haven't fully equilibrated yet. There is also intriguing evidence that these 1 micron signals are changing over time. This is from a paper from 2015 looking at one particular region, and this region's relative brightness at 1 micron went up and then went down. Now, these measurements are not great and very hard to do, but it's hinting that something happened there. Maybe a volcanic flow happened. We don't know. This is something that future missions to Venus are definitely going to try and figure out, because there's at least hints that things are occurring on the surface. And if they are, we'd be able to see a different of volcanism on another terrestrial planet that might be quite different from Earth, which is fascinating. Thank you for your time and attention.